All right, here's example 1 in section 7.2. We are going to do the same problem we did in section 7.1 involving the speed of an airplane affected by a wind. However, instead of using law of sines and law of cosines to find the answer, we are going to use component form of vectors. So here we've got the formula for the component form of a vector using sine and cosine and magnitude. So if we call the airplane itself vector v, which is going 175 miles per hour, and the angle, remember, was 40 degrees north, so north 40 degrees east. That's that angle right there. So if we're using this with our trig stuff, we need that angle instead. So from the x-axis to the y-axis, with that angle being 40, would mean that this angle is 50. So magnitude 175, angle from the x-axis counterclockwise, like we're used to, like we've been doing all year, 50 degrees. So then we have 175 times the sine of 50 for the vertical component. So horizontal component, vertical component. Then we have the wind vector, which we're using W. So that has a magnitude, the wind, of 35 miles per hour. This time we're going to use an angle of 330 degrees. Let me show you why. This was a 60-degree angle because our bearing is south, 60 degrees east. So if that is 60, and we need to know this angle all the way around here, then this would be 90, 180, 270 plus 60. So 270 plus 60 is 330. So that's our angle in standard position for our trig angle in standard form. Okay, so this is our component form for the wind vector. So together, if we add our airplane plus our wind vectors together, we get our resulting vector of the true speed of the plane and the true bearing of the plane. So that's our goal here. So adding the vectors together, v plus w should give us the resultant vector, which I'm calling vector r. So to do that, from what we learned last time, all we do is we add our horizontal components together. So there they are, that's a plus. 175 cosine 50 plus 35 cosine 330. And then we add our vertical vectors together. So 175 sine 50 plus 35 sine of 330. Okay, well, at this point, to find our resultant vector r, I'm just putting this in a calculator and giving 3 decimal places. It's not going to be 100% accurate, but it's close enough to show that we can get the same answer we got in section 7.1. So I put this whole thing in the calculator, make sure you're in degree mode, and you get 142.799. And then this whole thing in the calculator in degree mode, and you get 116.558. So next, we want to find the magnitude and direction of this vector, and right now all we have is component form for the vector. So we want to change our component form to the angle and direction. Actually, angle is direction, the direction and the magnitude. Okay, so to find the magnitude of our resultant vector, or the magnitude of v plus w, that's where we're doing the Pythagorean theorem. So square root of 142.799 squared plus 116.558 squared. Put that in a calculator and you get like 184.3. So let's just round that to 184 miles per hour. Then theta, the direction of the plane, we do our inverse tangent of y over x. So, or b over a, whatever letters you want to refer to for this. So our vertical component divided by our horizontal component, throw that in a calculator, we get 39 point something degrees. Now just remember that this is an angle in standard position. So this would be this angle right here that is 39 degrees. All right. So the problem with that is it's great if we're talking about the unit circle or putting angles on a coordinate plane in standard form where we go counterclockwise from the x-axis, etc. 39 would be a great angle. It's going from east to north. But if we are talking about navigation, then that is using a different system where we go from north to east instead. So this whole thing from north to east or east to north is 90 degrees. We know that this angle from east to the resultant vector is 39. We need the angle from north to the resultant vector. So we're just going to go 90 minus 39, which is 51 degrees. And then we rewrite our bearing as north 51 degrees east. So again, two different ways to do the exact same problem. We get exactly the same answer, whether we use law of cosines or law of sines following that, or if we just use our vector component form that we've been learning about in this chapter.